Hi everyone. Well, in the last few minutes of our previous lecture, we touched on section 1.3, where we're going to study integrals that lead to inverse trigonometric functions. And we did make one key observation, namely that while there are, of course, 6 inverse trigonometric functions, and therefore, in principle, we have 6 sets of integrals leading to those inverse trigonometric functions, the reality is that we can cut that number in half. And that's because the derivatives of the inverse trigonometric functions, they all come in positive negative pairs. And so therefore, while we could talk about, for instance, integrals that lead to both arcsine and arccosine, the reality is we only need to think in practice about integrals that lead to arcsine. We don't need to worry about integrals leading to arccosine, except in a very small number of cases that we'll touch on right at the end of this section. Same is true for arctangent and arccotangent. Same is true for arcsecant and arccosecant. So we can really just focus on 3 of the inverse trigonometric functions. So we're going to talk about integrals leading to arcsine, arctangent, and arcsecant, and that will be sufficient. So with that understood then, let's look at the first of those. Let's talk more about integrals leading to arcsine. And so, what we figured out just using our knowledge of differentiation at the end of the last lecture is that the integral of 1 over the square root of 1 minus x squared, that's going to be equal to the arcsine of x plus c. And again, that's because the derivative of arcsine of x is 1 over root 1 minus x squared. But there are some, I won't say problems with that statement, but there are some unfortunate aspects to it. Namely that it seems to be very, very restrictive. Because, for instance, if that constant 1 under the square root is any other constant, then all of a sudden this doesn't apply. And at minimum, we'd like to be able to deal with that. We'd like to know, well, if the integral of 1 over the square root of 1 minus x squared is an arcsine function, what about the integral of 1 over the square root of a constant minus x squared? Because in order for this result to really be generally useful, we need at least that minimum amount of flexibility in terms of how we apply it. Fortunately, we can answer that question. But in order to do that, we need U substitution. And in fact, that's why we've left this topic to section 1.3 as opposed to dealing with it back in section 1.1. So more generally, we have the following. So the first of our theorems for this section, we're going to state that the integral of 1 over the square root of a constant, and I'm going to write that constant as k squared, not just as, say, k, for reasons that will become apparent shortly. So the integral of 1 over the square root of k squared minus x squared, we're going to show that that's equal to arcsine of x over k plus c, and that's going to be true for any constant k greater than 0. Now, how are we going to do it? Well, in order to integrate that, presumably we're going to need to somehow apply that result for arcsine. They're close, and while it's certainly true that 2 very similar integrals in general could be integrated through very different methods, it seems unlikely that I'm going to start talking about integrals of inverse trigonometric functions and, in fact, state that the result will lead to an arcsine and not somehow bring in this basic result. So presumably we want to somehow manipulate this so that we can use that. And so then to begin, presumably the first thing we need to do is to get rid of that constant. So we could do that. We could factor it out. So we can rewrite that integral And well, we factor k squared out of the first term, then we'll have to factor it out of the second term as well, which is a bit awkward because there is no k or k squared in that second term. So that means that under the square root, we're just going to have k squared times 1 minus, well, x squared over k squared. So in some respects, that kind of makes the first term a little bit nicer, the second term a lot worse, but let's see if we can work with that. Now, that's the square root of a product. And unlike square roots of sums or square roots of differences, we can very easily rewrite the square root of a product. It would just be the product of the square roots. So then that's going to be the integral of 1 over the square root of k squared times the square root of 1 minus x squared over k squared. And because we've stipulated that k has to be a positive constant, the square root of k squared, that's just k. So that's going to be the integral of 1 over k times the square root of 1 minus x squared over k squared. Okay, well, sort of good, sort of bad. That k we can deal with pretty easily. We'd just be able to pull it outside the integral altogether since it's a constant. We could write that as 1 over k times the integral of 1 over the square root of 1 minus k squared over, or x squared over k squared, if it seems like that would be useful. But what do we do with that x squared over k squared? Well, because it's a quotient of two expressions, both of which are squares, we could at least combine those together into a single squared expression. So let's go one step further here, and let's say that that's going to be the same thing as the integral of 1 over k times the square root of 1 minus x over k all squared. But if we do that, then what we've basically got, although it's a little bit more complicated to look at than what we've discussed before, what we've basically got here, especially again if we ignore that constant k, is an instance of linear composition. This is our basic integral for arcsine, the integral of 1 over root 1 minus x squared, with the x replaced by something linear. So we could, in fact, apply our pattern for linear composition here, or because this looks a little bit more complicated, it seems a little bit less obvious maybe how we would apply it. Of course, we can always resort to u substitution. So I'm going to let u be x over k. So that du then, again, remembering that k is a constant, well, du would just be 1 over k times dx. And what do you know? We have a 1 over k times dx right there in our integral. So now the integral we started with, integral of 1 over the square root of k squared minus x squared, well, that's going to be the integral of 1 over the square root of 1 minus u squared times, well, 1 over k dx is our du, and that is exactly our basic integral for arcsine, but now written in terms of u instead of x. But so what? We know how to handle that. That's going to be the arcsine of u plus c, and then substituting back for u, we get the result we expected. We get the arcsine of x over k plus c. So that's where that comes from. So it's u substitution, or more simply just applying that pattern for linear composition, but in a slightly new context compared to how we've seen it before. But this is good. Now we've got a slightly wider range of integrals that we know will lead to an arcsine function. Let's do an example in the next video.